Obviously, the previous example we have seen in an earlier video about the introducing backpropagation using a very simple function with just two parameters. It's just basically testing the waters of backpropagation. Obviously, we need to go into a bit more detailed discussion about how backpropagation is applied in neural networks, and this section kind of covers some of the basics. Out of this section, in this kind of introductory, I think it's worthwhile going through an introductory example that involves just some kind of a very simple kind of neural kind of structure. In fact, I'll go through a structure that it will actually involve just a single neuron. So I'll just call it the single neuron backprop. And of course, we can actually go through over more and more complicated examples, but I think this is kind of sufficient to just apply backpropagation, what we have just learned on that video, to a bit more neural kind of networking setting. So the single neuron is obviously modeled by dot product. This dot product is actually shown over here, followed by some kind of non-linearity. Let's assume that there's non-linearity is the familiar to us sigmoid to produce some kind of prediction of the output. Evidently, this is a binary classifier, as we have seen earlier. Okay, and the question now we can ask is what about this gradient? The gradient of y hat with respect to the vector parameter, now w. And this is evidently, I mean, if I'm just giving you a simple example here where w will be 2 minus 3 minus 3, this will be the w0, w1, and w2 elements of this w vector, and x is going to be x0, x1, x2 equals to minus 1, minus 2, and 1. This will be the values of the x vector. Then we can actually ask the question, what will be the gradient of y hat with respect to w? And then evidently this is the partial derivative of y hat with respect to w0, with respect to w1, and finally with respect to w2. We would like to calculate this kind of vector. Okay, and this vector is evidently 3. It's a dimensionality of 3, as we have 3 parameters in our system here, 3 trainable parameters. So okay, so the computational graph here is fairly trivial, so we are not going to draw it again. It is actually given, shown in front of us. So the only thing we need to sort of understand is how, if you have all the tensor names, so obviously, evidently there's one tensor here, which is, we can denote it as z, and we are going to understand that we are going to backpropagate from y hat all the way to this tensor. So we're not really interested, it's quite important to recognize in backpropagation problems with respect to what gradients you need to calculate. So no one asked us anything about x, and therefore we are not going to actually go there. The only thing we need to do is to go here using the forward and the backward kind of passes. So the forward pass is actually straightforward. And the first equation here, again, using the principle of least dependencies, we are starting from the input of the network going to the output. So the first equation is z is equal to w transpose x. That's equation number 1. And the second equation is y hat. The equation 2 is y hat is equal sigma of z. That's equation 2. Okay. All right. So now that we have these two equations, we can actually, in fact, calculate all the values that we have in our system, and It's actually very easy to see here that this is 2 minus 3 minus 3 times the vector minus 1 minus 2, 1, which is evidently 1.0. And this one ends up being the application of the sigmoid that is now treated as an elementary function over here. That's the sigmoidal function. And this is, if you do the calculation, it's going to be end up being 0.73. Okay, so the forward pass is done. We have for each of the tensors that we are interested in the corresponding values, and now the backward pass starts. So the backward pass starts evidently from equation 2, and this is our first gate that equation 2 corresponds to, has the first downstream gradient with respect to this kind of grade, which is also the first gradient that we are going to calculate. So we will, just like what we did earlier, we denote with a small letter d in front of y hat. This is a partial derivative of y hat with respect to y hat, and this is 1.0. And the sigmoidal unit, we have seen it earlier in the previous kind of video, so we will call it as such as, if you remember that kind of template, the template kind of equally applies here. So according to this template, we have a gate which receives, it's in the forward pass we have, let's say, a vector, a tensor z, and x and y were the tensors, so it accepts a downstream gradient dz, and we need to calculate the dx and the dy. And the template that we have seen earlier, it is can be written as follows: the dx, the downstream gradient dx, is the upstream gradient dz that someone calculates for us, times the local, which is the partial derivative of the gate function dz with respect to x. And the same thing can be for the y. So this is, that's basically the two kind of sort of ports, the two downstream gradients that are going to be calculated. So the first, over here we have only one port with respect to this gate, so the dz is over here. So dz is the upstream, which is dy hat, with respect to times the sigmoid. The sigmoid is sigma of z with respect to z. Okay, so that sigmoid, that partial derivative we have seen earlier. So for those who have missed it, please go back to that elementary backpropagation video, and you should see that this gate is this partial derivative is 1 minus sigma of z times sigma of z, and this, if you do the calculations, is around 0.2. So that is my backpropagation with respect to this gate. Now I have calculated the downstream gradient, which evidently is going to be needed for the backpropagation of equation 1. So the backpropagation of equation 1 with respect to w, so we have now dw as the tensor. So dw is going to be the downstream, sorry, the upstream, the dz, times the partial derivative of the dot product of w transpose x with respect to w. All right, so this is going to be, well, this is reused from before, 0.2, and I am going to now have something we have never seen before. I have a partial derivative of a scalar with respect to a vector. That partial derivative is effectively a gradient itself, and it is partial derivative of, I will now expand the gradient of w0 x0 plus w, the dot product that is, plus w1 x1 plus w2 x2 with respect to w0. That's the second element, is, as you guessed it, exactly the same dot product. I'm not going to write it again with respect to W1. And the third one will be exactly the same dot product with respect to W2. That is my this partial derivative over here. And as you can see, I have something which is a partial derivative of a sum. This can be broken down into individual partial derivatives, and only one term out of this summation over here of partial derivatives is going to be of concern to me. It's going to be non-zero. So if I may expand it, it is 0.2. It will be partial derivative of W0 x0 with respect to W0, plus the second term will be 0 plus 0, because there's absolutely no W0 over here. So that will be all zeros. Similarly, the second element over here of this vector, it will be partial derivative of W1 x1 with respect to W1. There will be 0 plus that plus 0, and then finally will be 0 plus 0 plus the partial derivative of W2 x2 with respect to W2. Okay, so these are basically my this will be my the three elements of this partial derivative. So this one is going to be equal to 0.2. Well, the partial derivative of W0 x0 with respect to W0, if you can go back to that lookup table that we have recommended in the course site also to look up elementary partial derivatives, this will be simply x0. So it will be x0. The second one will be x1. And the third one will be simply x2. But x0, x1, and x2 are actually given. So it's very easy to calculate the final dW, which is minus 0.2, minus 0.4, and 0.2. And that actually concludes our backpropagation exercise. And in this case, we have been given, if you like, a very simple, it's a single neuron that is doing binary classification. We backpropagated it. And we are going to, in a from scratch implementation, plug in all these kind of partial derivatives in that code. And we can continue. In a deep neural network now, we will be facing, as we have seen earlier, for example, in this network that we have seen earlier on doing multi-layer classification, evidently there will be one or more kind of fully connected kind of layers. And people have gone into sort of, as your site kind of indicates, into and tabulated all of the gates. Now these gates are no longer gates which are been dealing with scalar quantities like an addition, multiplier, and so on, but they are involving now matrices and vectors. Let's say matrix and vector multiplication is a gate that we have seen earlier on fully connected layer architecture. So over here we are seeing a fully connected layer, which is just doing a matrix by vector multiplication, producing another tensor Z. And someone is asking us to implement, to calculate the partial derivative of that downstream gradient. I mean, this downstream gradient with respect to the matrix W. And people have actually tabulated these results as well, because they are very easy to symbolically tabulate them. And here is the response, the results. The downstream gradient with respect to W is the upstream gradient transpose that someone is giving you times the transpose of that vector X. And so we can actually use these tables. These tables have been tabulated in these two references in this PDF file over here. And this PDF file, if I open it, you can actually see all these kind of formulas and the source, what is behind this kind of table. So you can actually see the gate of that I just explained is a matrix times a column vector with respect to a matrix. So that is the fully connected layer architecture. Evidently, we have a nonlinearity, the ReLU nonlinearity that follows that. But with respect to this kind of gate, over here we are explaining where the final formula that we have seen in our nodes comes from. So you feel free to use these tables in any problem of backpropagation you will be facing. Although for this introductory kind of course, we will not be insisting on having, if you like, a deeper understanding or practice with respect to this kind of more complicated kind of networks. In fact, it's sufficient to deal with what the frameworks are actually using, let's say PyTorch or TensorFlow with the so-called AutoGrad and AutoDiff methods, and have an example, see an example of how they do it kind of numerically without really going into all these kind of complicated equations, but at least now you understand what is behind these kind of libraries. There is another page over here called Backpropagation Exercises, where you can actually see the exercise we have gone through, as well also some more complicated cases of having, if you like, non-linearities in the present in these kind of networks. Again, these are all exercises you can actually go very easily using the existing presentation, and anything more complicated is kind of outside of the scope of this course.